Assalamu alaikum everyone. Hope everyone is doing well at their home. In the last lecture, we discussed about the transients in the power system, and we concluded that we can make the transient equal to zero when we have the switching at current zero, and we can have a maximum transient when current is passing through the maximum value. Now we'll come to the representation of the power system. Actually, we'll see how different components of the power system can be represented. We know that our power system comprises of different components, and when we know their equivalent circuit, we can connect them. We can connect their equivalent circuit and then solve them. And by solving them, we can get what we want. So first is the synchronous machine. Synchronous machine is nothing but a synchronous impedance in general behind an excitation EMF. So if we neglect RA, we can see that it is a simple XS synchronous reactance behind excitation EMF EF. The direction of the current shows that this is the generator and it goes out from the EF and to the VT. VT is the terminal voltage. Similarly, synchronous motor is again the same machine. The only thing is that the direction of the current is reverse. In this case, we have the synchronous impedance. This is the excitation EMF. This is the terminal voltage. Current direction is like this, so that it takes the power from the system. And again, if RS is taken to be zero, it comes out to be only this circuit where we have only this synchronous reactance. So the transformer, as we know, it is represented like this, referred to primary. This is the primary resistance, primary leakage reactance, secondary resistance, secondary leakage resistance. Of course, this R2 dash, X2 dash referred to primary. This is the magnetizing branch. Neglecting magnetizing branch, as we know that when we do the analysis, we usually neglect the magnetizing branch. It is then only represented by this circuit referred to primary, where R1 is the R1 plus R2 and X1 is equal to X1 plus X2. And this I1 will be equal to I2 dash. That's why I have only written here I1. And if we take this as power, this loss less, in that case we can represent the transformer like this only. A reactance, series reactance between the two voltage levels. A transmission line, a short transmission line is represented by a series combination of the resistance and this reactance. And again, this is this separates the two voltage levels, V1 and V2, sending in voltage and receiving voltage. If we neglect the resistance, we can get this. If we have some capacitance as well, we can use the pi network or T network. In general, you can understand, and we know that in most of the cases we have and we represent, we neglect other components of the system. We include only these four equipments of the system. This you can say synchronous machine, generator, motor, transmission line, and transformers. Now, when we know the components and their equivalent resistances, equivalent circuits, and then we have a power system. We know where machine is connected or where equipment is connected where. We can use these equivalent circuits, connect them equivalent circuits, and then analyze the circuit. So for that, we need to first represent the power system. So by representation of the power system, we need a single line diagram. So what is a single line diagram? It's actually the representation of this power system and power system representation in steady state. I haven't written that in here, but you can understand it. We'll first just read out certain sentences. The single line diagram of power system network shows the main connections and arrangements of the system components along with their data such as output rating, voltage rating, reactances, and resistances. So this is general information about the single line diagram. We cannot say this is the definition. Usually we know that that our system is three phase, and when we solve our three phase or analyze our three phase, and we know that this three phase is a balanced system, what we do, we only do the per phase analysis. We only do the per phase analysis. We represent it by a single phase and a neutral return, and then calculate different parameters, whether it's voltage, whether it's current, whether it's power, and or whether it is this impedance, whatever be the case. and then accordingly we convert it to three phase. For example, if we have calculated the power, we can multiply the three to get three phase power. If we calculate the phase voltage in case of this star connected system, we can multiply root 3. Similarly for current in case of delta connected system, you know all these things. What I mean to say is that when we have balanced three phase system, we solved it by a single phase system with the neutral return. But in case of single line diagram, it's simply represented by a single line omitting that neutral return as well. We only represent our system by a single phase omitting the neutral return as well. And in that case, we use the standard symbols of different components which are connected in the system. And the prime condition for this is that the system should be in steady state, there should not be any transient, there should not be any abnormality, and the system should be balanced. In that case only we can represent a system in the single line, uh, or in the earlier case we were using them in a per phase analysis. So we can see that a three-phase network consists of a transmission line, generator, transformers can be solved as a single-phase circuit composed of one of the three lines, that is the phase, one of the three phases, and a neutral return. That is actually what we do previously. But in single line diagram, the neutral is also omitted and the components are represented by standard symbols. So as I have told you that we use the single phase, only one phase, neutral is also omitted, and the equipment that are present in the power system are represented by their standard symbols. I will just show you that. This is the single line diagram of a particular power system. This is a generator, this is a transformer, this is a transmission line, this is another transformer at the receiving end, and this is the motor. We can say it's a load. That's why we use the machine at two ends. That's why we don't. We can even if we have a direct load here, we can represent that load by simply we show that by an arrow like this. So for the time being, we can use the machine. After that, when we come to that, if we have a load, we can also show that in a particular way. This is a generator. Now, how the data is represented? First, it should be known that how it is connected. It is connected in Y, and its neutral is connected to ground through a reactance. This is a circuit breaker. This is a bus that is at this bus. This generator is connected to this bus, and from this bus, we had a connection to this transformer through this circuit breaker. And this transformer is connected as delta Y. Y is again, this Y side is again connected to ground, but directly it is known as solidly grounded system. And then we have another bus, and then from this bus we have connection to the transmission line, and at the receiving end we have a transformer delta Y again, and this neutral is also solidly grounded. And then we have a motor also have the similar configuration of that of the generator, that is its neutral is connected to ground through a reactance. The generator rating, it should also be given because this single line diagram is this actually. This is a single phase where we don't have any neutral as well. So, but it should be, these are standard symbols of different components, and it's also comprised with this rating of different components. For example, generator has 40 MV, 11 kV, but this 11 kV is not the EF. This is the terminal voltage of generator, as we have seen in the this equivalent circuit of this. X dash is the reactance of the generator, that's 20%. I will let you know what X double dash means and what 20% means. For the time being, you just remember this. This is the information about the reactance of the transformer. Sorry, this generator. That is XS, which we have already discussed. Motor, it is 30 MV, 11 kV terminal voltage, and its reactance is given like this. And transformer T1, that is this. It is also 40 MV, 11 by 220 kV, and these values are the line values, or we can say three-phase voltages. And its reactance, transformer reactance, actually, as we have discussed earlier, the transformer can be represented only by a single reactance, and this is the information about the reactance. Similarly, this is the information about the transformer T2. This is how this single line diagram is represented, and its data is also represented. Now, when we know the single line diagram of a system, we can convert it into the impedance diagram. What is actually impedance diagram? Simply representing the actual machine by its equivalent circuit and then connecting as per the connection. So this can be represented by like this. This is the generator equivalent circuit. This is the transformer equivalent circuit. as we have discussed earlier. And this is the pi model of the transmission line. These are the series parameters, these are the shunt parameters, and this is the equivalent circuit of the transformer T2, and this is the equivalent circuit of the motor. The current direction is this. That means this will be generator, and here the current direction is this will be motor. So this is the generator. I have shown it by the dotted lines where generator lie, transformer lie, transmission line lie, this transformer T2 and motor lie. This is known as the impedance diagram, where we don't omit anything, but we represent it by actual impedance, this equivalent circuit, and then connecting as per the connection. The connection is decided by the single line diagram. Now this is the impedance diagram. This is not more important, but impedance diagram shows how to connect the different components. The important is the reactance diagram. In this reactance diagram, what we do, we neglect all the resistances. Since the name suggests this reactance diagram, there should only be reactances. We neglect the magnetizing branch and line charge means capacitance. You can see that all the parallel components are neglected. This is the magnetizing branch of a transformer, these two, and these resistance from here to here are also neglected, and the capacitance also neglected. You will see that this diagram, this will be reduced to this diagram. It's very simple. After doing this, analysis of reactance diagram is very simple, and we particularly go for the reactance diagram, not for the impedance diagram. You can see here also that the information about the single line diagram given above is, you see only reactants are given, x double dash, x dash, x double dash, x in x. There is no resistance given, there is no capacitance given, there is no magnetizing branch given. That's why we always go for the reactance diagram. Now, before going into the, by concluding this impedance diagram or reference power system, so we conclude that we can represent a system, a power system by a single line diagram, and after that, by replacing the different components by their equivalent circuit, we use only the reactances of the different components, and we come to the reactance diagram. Now, solving this reactance diagram, you will see that we have two transformers in between T1 and T2. We need to refer it over here, or we need to refer it for with respect to this transformer. So, to overcome that, referring of a transformer, we go for a per unit system. This is the prime advantage of the per unit system, where referring of the transformer is eliminated. So coming to that point, we'll come to that after this. First, we'll define what the per unit system is. For a particular system, we have usually four parameters. One is impedance, voltage, current, and power. General power. It can be complex power, it can be reactive power, it can be active power, it can be apparent power. I will generally this call it power, and this power includes all the four powers. So we have four components. One is impedance, current, voltage, and power. So we want that all the components should be referred to a particular reference value. When we do that and we get the value of any parameter with respect to some reference, we say that it's a per unit value. For example, if we have a current, base current of 10 amperes and a reference value of the current of 10 amperes, and the actual current flowing through the system is 5 amperes. So the per unit value of the current in this case will be the actual value of the current divided with the reference value. With respect to the reference value, how much current is actually flowing through the system, that is 0.5. In this case, we are referring it only to 1. We can say 1 because we are simply dividing the actual value by the base value. You are quite familiar with the percentage value. We do the same thing, but after this we can multiply this by 100. We multiply this by 100, we get the percentage value. It means we are getting the essence that how many marks or how many we are getting out of the 100. So in this case, we are getting the value, how many, what is the value of a particular parameter out of 1, not out of 100. That is why it is known as per unit. Unit means 1. If we have a percent system, cent means 100, that it will be out of 100. So in general, we can say that we express the value of any parameter with respect to some reference value. And one more important thing is that this reference value or base value, x is a variable which takes any of these four values, whether impedance, whether current, voltage, or power. So this these two quantities should have the same unit. That means actual value of the current, reference value should be current. Actual value of the voltage, reference value should be voltage. Actual value of the impedance, reference should be impedance. Actual value of the power, reference should be power. So we have to take this into consideration, and we need to take care of this. And when this happens, you will see that its unit will be same as that of this. The overall unit of x per unit will be unitless. It will be dimensionless or unitless. So in general, we can define it x per unit will be the x in actual value divided by x reference or x base. Or we can say x divided by x base, and this is unitless. This is the general overview of the per unit system. Let us see how do we use it. First, we'll go through advantage of the per unit system. I will first read out the second advantage. As I told you, why we do it, what is the main reason? The main reason is the transformer referring, that is eliminated. For a circuit connected by the transformer per unit system is particularly suitable. By choosing suitable base kVs for a circuit, the per unit reactance remains the same referred to either side of the transformer. Therefore, various circuits can be connected by the reactance diagram. So what does this mean? It means whether we refer this transformer to primary or whether we refer it to secondary, we get the same value of the per unit reactance. So when we do that, we don't have to take care of whether we are referring it to primary or secondary. That's why in general we can say that the referring problem of the transformer is eliminated. That is one advantage, and it is a prime advantage of this. The second one is that the parameters tend to fall in relatively narrow range, making erroneous values conspicuous. The per unit system provides a method of comparison. These are actually two. One is that the values come very narrow in the system where we don't use the per unit value. You will see the value can change from 0 to any value. Let's say 765 kV, 0 voltage to 765. It's a narrow range, but in case of this per unit system, it will change from 0 to 1 only. And this we can say this range is very compact, and we can compare it easily when we have two voltage level, and we know for a particular system, for a particular good power system, the voltage regulation should not go beyond 5%. That means voltage should not go 0.95, it should not go beyond, we can say below 0.95 per unit and above 1.05 per unit. You can see the voltage will be in 0.95 to 1.05. It means it's a narrow range. We don't have to look for the other actual voltages whose range is very high. We can see for normal system it is from 220 volts to 765 kV, which is in India. So but in case of per unit system, it will only vary from 0.95 to 1.05 per unit. And there are some drawbacks also. Factors root 3 and root 3 are not root 3 and 3 are not there, but sometimes we can add them. These drawbacks are not uh, those high drawbacks that can overcome these advantages. And phase shift does not come into play. This also is not a hard and fast rule. Sometimes phase shift we can also use, but in general we can see that phase shift is not there. But you will see that phase shift as we want, we can also use this phase shift and root 3 and 3 also in that case, particular case. So now comes the question, how do we calculate this per unit values? And when we calculate the per unit value, we first have to select the base. The base actually is selected first. Voltage and rated MVA are chosen to be as base, or we can say reference value. So SB is the MVA rating of the system or any equipment, and VB is the rated voltage of the equipment, and they are deliberately taken to be the base value. It becomes very similar, very simple. If we take any other base also, we can use that also, but we cannot compare it actually with the actual value. But it is advantageous to take the ratings of the machine as base value. What is the rating only? That is MVA rating and this voltage rating. From these value, for a single phase system, we can calculate IB, that is the current, that will be equal to SB divided by VB. Similarly, this ZB, that is the base value of the impedance will be equal to VB by IB. By putting the value of IB from here, you can get VB square by SB. So these are the four base values. As I have told you that we need to calculate four parameters in per unit. First, we have to choose the base values of these four parameters. SB and VB are taken to be the MVA rating, and from these we can calculate the base value of the current and base value of the impedance. So when we do this, what is the actual value of the base, actual value of the per unit impedance? That is equal to the actual value of the Z in ohms divided by this Z base. So the Z base will be equal to VB by SB square. When we put it here, it will be equal to Z into SB divided by VB square. In general, the Z per unit will be equal to Z in actual values multiplied by SB divided by VB square. This formula will give us the value of this Z in per unit. And all this is in the single phase system. If we have a three-phase system, in that case, ZB will be equal to SB divided by root 3 divided by VB. This is the actual value, this is not the per unit value. So ZB will be equal to phase value divided by phase current. That will be equal to VB divided by root 3 divided by IB. So when we put the value of IB from here, this root 3 and root 3 cancel out. It will be equal to VB by VB square by SB. So Z per unit will be equal to Z actual into SB divided by VB square. Here also ZB is same. As of this, you can see it from here. ZB here and here is same. Whether it is a three-phase system or a single-phase system, you can get Z per unit same. There is no difference. Now sometimes you are given the value of Z per unit in one base and you are asked to calculate in another base. Because from this expression you can see that if base values change, this per unit value of the Z will change. Actual value will not change of course. So when this happens, you can see Z per unit 1 is equal to Z into SB 1 divided by VB1 square. Z per unit 2 in the second base we have a different value. That's why I have written here subscript 2. So it will be equal to Z into SB2 divided by SB VB2 square. Then we divide this equation by this to Z per unit 2 divided by Z per unit 1 is equal to SB2 divided by SB1 divided by VB1 by VB2 ka whole square. So Z per unit 1 will be equal to Z per unit 2 will be equal to Z per unit 1 into SB1 by SB2 by SB1 into VB1 by VB2 ka whole square. This is the formula of the new per unit value of the impedance if earlier per unit value is given for a particular base, these two bases, and now these two bases we need to calculate it. Now coming to this was about the change of base of the current, change the base of this impedance and how this impedance will change. Now we will come to per unit impedance of a two-winding transformer. We will calculate the per unit impedance of two-winding transformer first, referring to primary, then referring to secondary. Now when we refer it to primary, we need to have a base value of voltage as V1. We need to keep this in mind. Let us say SB is the machine rating and VB is the again its rating, and which is V1. V1 is the rated voltage. So it is ZB will be equal to V1 square by SB. So you need to keep this in mind. When we use the per unit impedance of the two-winding transformer, when we refer it to primary, let us say this is primary, we need to take the base value of the voltage as V1, that is primary voltage. So here we take it as a V1 by SB square. Now, what will be the value of this R1 per unit? It will be equal to R1 per unit will be equal to R1, actual value of the R1, multiplied by SB divided by V1 square, that is this value. We need to divide by ZB. Similarly, X1 per unit will be equal to X1 into SB divided by V1 square. So this is quite simple. Now here, since it is referred to primary, this will be equal to A square into R2, where A is this winding ratio of the transformer, which is, we can see it will be equal to V1 by V2. You can see it from here. A is equal to V1 by V2. So first we will calculate this, what is its actual value in terms of V1 by V2. A square R2 per unit will be equal to V1 by V2 ka whole square into SB divided by V1 square, that is this ZB, multiplied by R2. R2 is the actual value. So this V1 and V1 will cancel out. It will be equal to R2 into SB divided by V2 square. It will be like this. Here it comes out to be R1 X1 SB divided by V1 square. It will be V2 square. Similarly, for this case, you will see it is A2 X2 per unit will be equal to V1 by V2 V1 by V2 whole square or V1 square by V2 square into SB divided by V1, that is the ZB, into X2. It will be equal to X2 into SB divided by V2 square. So I hope you understood this. So Z1 per unit will be equal to Z1 into SB divided by V2 square, V1 square, that is this R1 plus X1 per unit, that is R1 plus X1 into SB. Z1 is equal to R1 plus JX1. So Z2 dash per unit will be equal to, in general, when we talk about this impedance, this is the individual R and X1. This is in combination, that's R1 plus JX1 or root of this, whatever be the value. A square Z2, that is Z2 dash per unit into SB1 by SB divided by V1 square, V1 square by V2 square into this, it comes out to be equal to Z2 per unit will be equal to, that is referred to primary, will be equal to Z2 divided by SB divided by V2 square. Now coming to the same circuit, but now we will refer it to secondary circuit. You can see this is 1 by A square R1, 1 by A square X2. This is X1, X2 R2. This is 1 by A V1. This is V2. Now in this case, since we are referring it to secondary voltage, we need to choose the base voltage as V2. This is very important. Here we choose the base value of V1. Here we have to choose the base value as V2. So ZB will be equal to V2 square by SB. So when we do this, we first calculate the per unit value of this. It will be equal to 1 by E square R1 per unit. It will be equal to V2 square by V1 square into SB divided by V2 square. This V2 square will be cancelled out. It will be equal to R1 SB square by V1 square. You can see it from here. This and this is same. Similarly, for this X1, you can calculate this on your own. It comes out to be X1 SB divided by V1 square. Again, this is same. So R2 will be equal to R2 into SB square by V2 square. X2 will be this X2 divided by SB divided by V2 square. You can see these are also same. So in general, you can see here Z1 per unit is equal to 1 by A square Z1 into SB square by V2 square. So Z1 dash per unit will be equal to V2 square by V1 square into Z1 into SB divided by V2 square. This V2 square and V2 square will cancel out. Z1 dash per unit, that is Z1 referred to primary, per unit will be Z1 into SB divided by V1 square. That is the same. You can see it here. Similarly, we can prove that Z2 per unit will be equal to Z2 into SB2 divided by V2 square. That's again same. So in general, we can say that Z1 per unit will be equal to Z1 dash per unit, or Z2 per unit will be equal to Z2. So Z2 dash per unit will be equal to Z2 per unit. So what will be the case? You will see that Z1 per unit will be equal to Z2 per unit, that is referred to secondary. But why we need to take one precaution here, that when we're referring it to primary, we have to take the base value of V1, and when we refer it to secondary, we have to take the base value of V2. What I mean to say is that when we are solving a circuit, on primary side base value will be V1, and on secondary side base value will be V2. So this is the important point that you have to take into consideration while calculating the per unit value of the transformer or a transformer in a power system. So I hope you understood it. Thank you very much.